All right, welcome on in. Looks like we're more or less ready to get started here. Hopefully we pick up a few people. So let's see. For starters, let's see, Tuesday. Sorry, I was all prepared and then I got an email right before we started here, so kind of my mind shifted to something else. So yeah. I will be showing you, not at the moment, but I will be I'm going to be showing you stuff all class, but I will be showing you quite a bit of math today that you're going to want to see. So you probably would want to jump into the YouTube stream so you can see that stuff. But as always, consume it how you want, but there's going to be plenty of visuals going on today where I'm showing you stuff. So for starters, I want to talk about the schedule going forward because we're about to transition, right? So if you're on the main Ventura College webpage and you go up to the academic calendar, then obviously you can get to the academic calendar. Notice here the big sign on the website, wristband and mask. So just as a reminder, that's kind of part of what we're talking about. I know some of you have heard me talk about this before, but now we're at the point where it's going to happen. So I kind of need to go over all of it again so we can try to reduce the amount of friction that we'll have when this happens. We have a relatively small class at this point, so hopefully it's fine going forward. Hopefully we won't have an issue, but I just kind of want to go over it so everyone's on the same page. So today is the 8th, right? We are the 8th. So it's this Tuesday right here, February the 8th. This one right here. Next one, the 15th, we will be on campus. Okay, so regular classes resume on the 14th. Well, they resume on campus the 14th. So if you have a class that was registered to be on ground, the meetings will start taking place on campus. Okay, so that means a couple of things. One, remember this is a hybrid class, so we only meet in the classroom half as often. The rest of the material you find in Canvas. So that's like the videos that you're watching in the different sections. So instead of coming to class for another 2 hours, actually 2.5 hours of lecture, you're watching videos online, that kind of stuff, okay? So kind of keep in mind that you're in what is called a hybrid class, and there's lots of different versions of hybrid. But the main one that you see on campus is where basically it's 50% the meeting class time, and then 50% of it is pushed to the web. So that kind of makes sense why I can't cover everything in class. 50% of it is videos that you're going to be watching along the way, and half of it is us in the classroom talking to each other and answering questions and me teaching you things and figuring things out and stuff like that. So today, the 8th, we are obviously still online. The 15th, so a week from today, we will be meeting in the classroom. Your schedule says what classroom it is. It's Science 230, but your schedule will tell you that as well. Okay, so we're going to meet there. That means you have to be able to get on campus. I know I've already talked about this, but I'm doing it again so that everyone has full knowledge and that there's no confusions or mix-ups on day one. To get into the classroom and to be allowed to stay in the classroom, you have to have two things. You have to have a mask and you have to have a wristband. Okay, the mask you'll bring yourself. Either one of those things, if you don't have, I have to ask you to leave. Also, if you show up and you're coughing and stuff, I have to ask you to leave. Part of my responsibility in the classroom is everybody's safety. And if we have someone who is potentially spreading some kind of illness, especially now under these kinds of conditions, I have to try to remove that health threat from the room. That's part of what I'm supposed to do. So showing up with a mask, showing up with your wristband, and then not being sick yourself, right? Now, it's hard because if someone is asymptomatic, they don't know. They don't even have any clue they should go get tested or anything, right? You don't have any symptoms. Hopefully that doesn't happen. But if someone is showing up with symptoms, we have to ask them to leave the classroom. That's just sort of how it goes. So So how do you get those things? Well, a mask, we're a couple years into this, so I'm sure everyone understands the concept of having a mask in their pocket when they leave the house. But the wristband, what do you have to go through to get to the wristband? So on campus, there's a few stations. There's one in the west parking lot, which is near the classroom. You'll see like a little tent, like that, like they have at the market. It's a little tent like that, and you can actually drive up to it. Or at least that's how they've had it set up. I don't know how they'll have it set up next week, but that's what they've been doing because there's very little traffic so far. Starting next week, we'll start seeing more traffic. So what you do is on the VC app, hopefully you've already submitted your vaccine card. If not, do it now. You don't want to do it day of because that I don't know how long it takes them to approve it, right? Could be short, could be long, and then you won't be getting in the classroom. So inside the VC app, there's a part where it says you can submit your vaccination card. Basically, all it does is you take a photo of your vaccine card. It uploads it. At some point, the school will approve that. And then whenever you come to school, they'll know, oh, this person's vaccinated, right? So just upload it now. Don't try to do it the day of. That could be problematic. So get your vaccine card uploaded, and then the day of, you'll come to campus. There's a screening center in that it's the east parking lot where the market takes place, which is right near the science building. And next to the science building, there's that kind of orange building with the weird walls that you can see from Telegraph. They've been having a screening center there as well. So whichever way you're coming in, if you go to one of those screening centers, they're pretty close to the science building. Okay, so you'll go there. On your app, you're going to press the daily screening form or something it's called, and it's going to say, do you have any of these symptoms? If you have no, be honest with all these questions. If you don't have any symptoms, hit no symptoms. If you have symptoms, then obviously say you have the symptoms. And then it's going to say, have you knowingly been exposed to anyone who has COVID, right? And then you have to say, either yes or no. So I'm not sure. You all have varied backgrounds. I don't know if some of you are actually working in the field right now. If you're around people who are having COVID. So I don't know. But you want to answer that question, obviously. If you've been exposed to people with COVID, answer it honestly. And then if there's no reason to believe you're a danger, then the app is going to say you're approved. If your vaccine card has been accepted, then the little screen it shows you will be blue. That blue indicates to whoever looks at it knows automatically, oh, this person's vaccinated. Okay. Otherwise, I think it's maybe orange or something, but it won't do you any good if it's orange because you're not vaccinated. So then what you do is you go to the screening station where the one in the parking lot has had a tent. The other one over by the orange building has sometimes had a tent. Sometimes they've had them inside. They kind of keep changing it over there. But you just go there. It should be obvious. Show them your phone with the little blue screen that says, this is your pass for today. And they'll give you a wristband. The color of that wristband changes every day. You just need the one for Tuesday because that's the only time I see you. If you have other classes, then you have to work with those other classes and go on those days. But they'll give you the wristband, and then you're free to come to class. I have to get the wristband. I'm not allowed being on campus without a wristband. You are not allowed to be on campus without a wristband, other than to go right to the screening station, right? You can walk 200 feet to the screening station, but you can't go to class. If you show up to campus, to the classroom, and say, oh, don't worry, I've been vaccinated. Sorry, it's not my call. You got to go. Right. And like I've said before, I actually agree with all these protocols, but also even if I wanted to, I can't change the rules. So please, I don't want to have a discussion about anti-masking or anti-vaxxing in the classroom on the first day. I can't do anything about it. I'm not the one you want to talk to. Go to the school board, talk to them, go to the school board meetings, voice your concerns with them. I don't make those decisions. I'm not on that pay scale to make those kind of decisions. So you'll come to class, you have your mask on, you have your wristband on, and then class should be fine. If you don't have one of those things, I have to have you leave. You're not allowed to be on campus if you don't have the wristband or the mask. You have to have both of those things, and then everything should work perfectly fine. Okay. I don't know what it's going to be like the first day back. First day of school on campus is usually nuts, but it's a little different because people aren't really trying to add classes the way they are the first day of class. And as far as parking's usually crazy the first day, but many of our classes are still online, and even the ones that are not all online, most of them are hybrid, like this class where we used to meet twice a week. Now we're meeting once a week. So it could be that when we go on Tuesday, there's going to be plenty of spots in the parking lot, or maybe it'll be like the first day of school where it's packed. I don't know. We've never had this situation before, so I don't know what it's going to be like. I would highly recommend, since we are a 1 o'clock class, I wouldn't suggest, at least on the first day, don't pull into the parking lot at like 12:58. You're going to end up being late, and that's just sort of, you're going to miss stuff. It kind of holds us back in the classroom. I don't know how long it's going to take you to get through the screening station. If one of the things that tends to happen on campus is crowds happen all at once because 95% of students wait till the last minute they can. So 1 o'clock classes it's a popular time. We have a lot of classes that start at 1. So if you go at like 12:58 to the screening station, you might be behind 100 people or hundreds of people waiting in line. A lot of times what happens at campus is if you're even just slightly non-procrastinator, so you're even there like 10, 15 minutes early, sometimes you miss the whole rush. And then like after you go there 15 minutes to 1, and then there's almost no one in line to get screened, and you get screened, and then you're walking back to the building and you look back and now all of a sudden there's 100 people in line. Like that's just how it works. Like you got hundreds of people that need to do something at the same time, and they've all waited till the last minute. Usually, sometimes even being 10 minutes early can help you skip like a ton of that kind of stuff because everyone else is waiting till the last minute. But it's up to you, but and how you do things. But I would recommend at least the first time, kind of get there 10, 15 minutes early at least, more if you want. But at least 10, 15 minutes early so you can just kind of see how it goes. And like hopefully you're not, 200 people behind in line when it's when class is about to start. We don't know how the stations are going to go. They haven't told us if they're like doubling the stations or anything like that. So we kind of don't know. I wouldn't wait till the last minute. And then you'll come to class. So remember that Science 2:30. So science, it's kind of weird. Science 2:30 is actually on the ground floor. A lot of time, if you're coming from the parking lot, a lot of times in a 2, you think, well, that's the second floor. But the science building is weird in that if you're on one end of it, the floor that touches the ground is the second floor on the other side of the building because it's on a slope. There's a slope there to that side. So it's a little deceiving. So 2:30 is actually pretty close to the parking lot. It's not very far away. In fact, it's pretty close to my office. I forget if it's on the same side of the parking lot or the opposite side, but it's on the part of the building that's near the parking lot, okay? So it's not very far away. And then we'll go in there. I do plan, I don't remember if 2:30 is one, I don't remember if that's one where I can reach the windows or not, but if I can, I'm going to open the windows so we get some ventilation in there. So, just if it's cold, bring a hoodie. If it's warm, then, dress. It's not like the rooms have a ton of air conditioning, but dress, don't overdress if it's warm, because I will probably open the door and or windows depending on what we can do in there. So yeah, is there any questions on getting any of that set up? And be better to talk about it now rather than have people have trouble later. No, we're good. Okay, so then we'll be meeting in class and moving ahead from there. All right, then if there's no questions, I will actually, a good time to take roll. Let's do that. Okay. If you're on the YouTube stream, can you just throw in your first name and last letter of your first name so I can keep track of that? Okay, so and I think I mentioned this. I don't know. I've had to say this a couple times in the last 2 days. So there won't be the Zoom recordings anymore. So you kind of have to come to class, or you're going to miss out on that material. Okay, because I don't have the facilities to conduct a meeting both on Zoom and on ground. We've tried experimenting with that, and it's a disaster. It's absolutely a mess. So didn't go well. So I have the good stream set up at home. I can stream well from here, but once we go back on campus, there won't be a recording of the meeting. So you really want to come. And this is a class where I think missing classes is really gonna hurt you. So also, so we'll get in the classroom. We'll be good. We'll get to know each other a little bit. We can have a little bit more back and forth rather than just me talking for 90 minutes. And, I can find out a little bit more about the type of people in the class and stuff like that. That'll be helpful. This class has gotten kind of small. We started off with like 19 people, and then now we've had some people drop along the way. We had some people that signed up for the class, and then they kind of don't like the idea of having to wear a mask or be vaccinated. So we had some people drop over that. So I think we're down to 12 people, so kind of a small class. Our classes that are not fully online are just not filling the way our online classes are filling. So that'll be a thing that we kind of study in the next few years and figure out how many classes of each type we should be offering. And we'll see how that goes. So anyways, so to the mathematics. All right, so we talked about this. Let's see, what was I saying? We got 8, and then the 15th we're meeting on ground, and then we're going to try to be finishing up. We're going to try to be through the algebra by like early March. Okay, we're going to see how that goes. So end of February, early March, I'd like us to be largely through the algebra because we have that Math for Meds book that we need to get to. And, the truth is a lot of what you're doing comes from that Math for Meds, so I want to make sure we have plenty of time to cover that book. And I've got things squared away as far as getting that all lined up, and we can talk about that in the coming weeks. But we have a few weeks before we need that. But I think everything for that part of the class is good to go and streamlined finally. Okay, so with that said, let's jump into it. Let's see. I don't think I need this open anymore. Don't need that. Okay, Delta Math. Okay, I got to move stuff around. Here we go. Okay, so you have some upcoming homeworks, and you've got one that is, so you've got this rational equations and rational expressions. And here's the deal with these, right? This is that part where we only meet half as much as an on-ground class. There's stuff that isn't going to get covered in regular class. It's going to get covered in the videos associated to the class. So rational expressions and rational equations are one of those. There's 2 reasons for that. One is it's really cumbersome to try to typeset these things in a way where it looks nice live. Like as I'm talking about it, it takes these things are fractions of polynomials. So think about being in a Word document and trying to make a fraction of polynomials. It takes a little bit of time, right? And the program I use is faster than a Word document, but it still takes some time to get those things to work right. So it really slows down the discussion. And the other thing I found is the videos are about as good as what I would say in class anyways. So if you just watch the videos that I've posted on Canvas, you watch the videos that accompany the homework, it's as good as what I would tell you right now if we talked about it in class. So that's one where I feel comfortable offloading it. I'm not saying it's an easy topic, but the examples that you're going to watch in the videos it's the same as the examples I would do right now. So in that case, I think we should shift our attention to other mathematics that is more helpful for me to bring up, where I can add context and background and make sure we have a solid foundation, okay? So just be aware of that. But by all means, if you send me questions on these, I can maybe talk about them next time. But be specific. Like send me a screenshot of the problem that you're having trouble with, or say, give me the name, like when it's, rational equations level 3, I'm having trouble with those. And then tell me like, oh, I'm trying to do this and it keeps not working. And then I can try to figure out how to help you. Okay. So the rational expressions, in fact, let's go to where are we? let's go into Canvas. So we talked about factoring, I believe, last time. And so now we're into rational expressions, rational equations. And like I say, watch the videos, right? So there's plenty of videos showing you how to do these different problems, walking you through it. Watch those. And we're going to get into systems of equations. Okay, we got to work through these systems of equations and make sense of it. I know it seems like we're going fast, but like this class has a ton of material in it. And again, being hybrid, we only meet for half the time that an on-ground class would meet. So it seems like we're really cramming it in because we are, right? We're cramming the material in. So I'm going to talk about systems of equations because this one, it's helpful to have a little more of the context that I can give you than with rational expressions. So I'm starting this right here. Let's see, it's up and published for you. Should be ready to go. This is the right section, right? 48, yeah. This is the right section. I have a Monday class and then a Tuesday class of this, and so sometimes I end up looking at the wrong Canvas page, so I just had to make sure. So we're going to go over systems of equations, how they work, what you're going to do. Systems of equations are hugely important. Every area of research out there, every type of business, everything, like systems of equations are being used in those areas, right? That doesn't mean everybody's using them because a lot of people don't learn math, and if you don't learn the math, then you can't use it to help your business. But there are many, many situations where systems of equations come in very handy, and sometimes it's the only way to solve a problem is to go through these systems of equations, okay? But it can be confusing and overwhelming at first, so I'm going to take a step back and sort of remind us of a few things to get us ready for when we actually jump into the system of equations here in a little bit. It's not going to overwhelm you because I know one of the things that people struggle with is graphing. Well, we're going to be using graphing. In fact, for this chapter, most of what we understand is going to be from looking at the graphs of things, and it's going to help us make a lot more sense when we're doing the algebra, because hopefully what happens is when you're doing the algebra and you're like, wait a minute, what's happening here? Like in your brain, you'll get an image of one of the pictures that we looked at of a graph. You go, that's right, it's no solution, and then you can answer it correctly. This is a chapter, and this happens in a lot of chapters, and in general, I don't recommend learning math by memorizing everything. You have to memorize some things in a math class, but the problem is I see a lot of people coming through the K-12 system where they've just learned that they should be memorizing everything. But that's not really math at that point. You're limiting yourself. You're holding yourself back if you memorize everything, because what you want to do with mathematics is memorize the essentials. Like, when we get to the quadratic formula, it's just the thing a person should probably have memorized. Like, there's a couple things to memorize, but really you should be understanding the material. So your guide through the problem should not be, I've memorized how to do this problem, because then what happens when life or me or whatever changes the problem slightly? And I see this all the time, right? I've memorized how to do this problem. I went home and I did 20 of them. Okay, what if I change it slightly to this other thing? I don't know. I haven't done those problems yet. That's not very helpful as a skill if you think about it. Like, what have you really learned in that process? So what you want to do is memorize the few things that are really important to memorize, but by and large, you want to be understanding the material. You should be able to think your way through a problem by understanding it, right? So, for example, there's 3 types of outcomes, 3 types of solutions that you can get when you're doing systems of equations. You can get what we're going to see most of the time, which is where you get a single solution. But other times you can get no solution, and sometimes you're actually going to get an infinite number of solutions. Now, what I see a lot of times is students memorizing when you get no solutions and memorizing when you get infinite number of solutions, but there's no real understanding behind it. There's no context that helps you make sense of it. And that's problematic because it means you can't really use it in the real world because you don't really understand what you're doing. But oftentimes it means you get the problem wrong on the test, because I'll see this where students do a bunch of work, exact wrong conclusion, because they're working from memory rather than understanding what they've written on the page. Okay? memorizing mathematics without understanding is pointless. It makes all the work you do for the entire semester, like you may get your passing grade if you can do it just right, but you're never really going to be able to make sense of that information or use it in any kind of meaningful way because you don't understand it, and you're just going to forget it. Things we don't understand, we forget, right? Your brain's like, I don't know, we needed this for the test, and we don't really understand it beyond that, so now the test is over, let's dump this information, right? And some of you may have noticed that. After the test, I can never remember anything. That's because you just memorized it and you don't really understand it, okay? So systems of equations is one of those where really try to understand it, right? There are some sections where it's like, yeah, you end up memorizing some stuff, but try to understand when you can. Okay, so we're getting into two variable systems. What does that mean? Well, so far we've been dealing with equations, and we've even looked at two variable equations. So you remember these, right? You graphed these in Algebra 1, although I see people be very kind of weak with these. So let's just remember, what if I want to graph y equals 2x minus 3? So there's the line y equals 2x minus 3. Let's make this a little bolder there. Okay, well, how would I do that? How did I graph that line? Well, I did it because I just put it into Desmos. But in general, how would you graph a line? On your homework, how are you going to graph a line? Well, there's a couple ways to do it. One is you want to look at this line and recognize that it's in slope-intercept form. So the number that's on the x is the slope, and the number that's on the end, the constant, that's your y-intercept. So what you do is, this means that the line goes through 0, negative 3, because if you plug in 0 for x, you get y equals negative 3, right? And sure enough, our line goes right through here, 0, negative 3. Then what do? Well, our slope is 2, and remember, slope is rise over run. So that's a rise of 2 and a run of 1. So that means I start here. I'm going to go up 2 and over 1, and that puts me right back on the line. And then you have 2 points, and you can draw a line through it. Okay, that's one way to do it. The other way is to make yourself a table. So what you do is you just pick some x values. How about just so you can see why the intercept exists, let's put in 0 for x. Okay, if I put in 0 for x, I get y equals negative 3. Okay, so this is negative 3. Okay, it plots that point. What if I put in 1 for x? Okay, 2 times 1 minus 3 would be negative 1. All right, what if I put a 2 in here? 2 times 2 is 4 minus 3 is positive 1. So see how I'm just plotting some points, and then you would draw the line through those points. Okay, that's two ways to graph a line. One is think about it in terms of slope-intercept. That's a very conceptual way of graphing it, kind of an advanced way of graphing it. Or you can plot points. Either one is fine. It's good if you can do both, but if you can only, if you do it one way, preferably, then whatever, that's fine. Okay, but let's ask ourselves, okay, who cares about that line? I know it doesn't mean anything to us because I just made it up, but why do we graph a line in general? Who cares? So what if I can graph a line, right? Well, again, you want to conceptually understand what the graph of a line is, right? And we kind of think about it like it's a solid object. I could reach out and pick it up and I would have this straight line in my hand. And that's fine if you think about it that way. But we also want to understand that a line is really an infinite collection of points. There's an infinite number of points on this thing, right? And I can even hover over some of them and it shows me all these different points that lie on this line, right? An infinite number of points. And what do those points represent? Well, those points represent coordinates that are solutions to this equation over here. In other words, each one of these is an x along with a y that when I substitute them into this equation, it makes the equation true. So let's look at this point right here, 1.5 comma 0. So if I plug 1.5 in here for x, I get 3 minus 3 is 0, and my y value is 0. Yeah, that's true. That works. Okay? So any of these points you pick on here, and you plug them into the equation, they'll give you a true statement. Okay, that's what the graph of a line is. It's just a visual representation of the solutions. So you can look at it and go, oh, that's where the solutions are to this equation. And then you can pick the one that you like, the one that works for you. Okay, so that's just kind of your quick reminder of what the graph of an equation is. It's a visual representation of these solutions. Okay. Well, that's fine. Why are we talking about that again? We did that back in beginning algebra. Well, what we're talking about now is systems of equations. What does that mean? What is a system of equations? Like what does that mean? Well, all it means is we have more than one equation at once that we want to satisfy. So right now we're talking about solutions to this equation. But imagine we had two equations and we wanted things that satisfied both of those equations. I want to find a solution that fits two equations at once. Okay, so let's just make up another one. How about this one? Let's change the color so I can call them red and blue. Okay, so we now have two lines. There's our system of equations. We've graphed it. Okay, that's helpful. We graphed the system of equations. Okay. So what about that then? What would the solutions look like to a system of equations? We want to find solutions that satisfy both of these equations. Okay, well, if we just look at the red line, then all the points on the red line are solutions to the red equation. And if we just look at the blue line, all the points on the blue line are solutions to the blue equation. So do we see anything that would probably be a solution to both equations at the same time? Well, then it would have to be a point that lies on both of the graphs. Do we see a point that is on both of these graphs at the same time? Yeah, it's the point of intersection right here. 2, 1. That satisfies both of these equations, and it is a point that lies on both of the lines. So let's just double check. 2, 1. If I plug in 2 here, I get 4 minus 3 equals 1. Yeah. Okay, what if we plug it in here? 4 plus 3 equals 7. Yeah, it works. So we verify that it is in fact a solution. That'll be really important, especially when we get to the algebraic portion of doing this. It's very easy to make a mistake, but the good news is checking your solution is much easier. Checking your solution is much easier than finding your solution. So that's good because like in Delta Math, when you get it wrong, you have to do another problem to make up for it. If you check your work first before you put it in there, you know 100% it's going to be right. Okay? Sorry, let me grab a water. I'm getting the hiccups because I'm talking so much and getting dehydrated. I'll be right back. Okay, sorry about that. Okay, so when we graph a system of equations, the point of intersection is the solution to the system because it's a point on both lines, and the points on the lines are the solutions to that line. Okay, so everything on the red line is solutions to the red equation. Everything on the blue line, solutions to the blue equation. The point of intersection is both. So that makes solving systems of equations pretty easy. I don't know, I throw them into Desmos. This tells me the answer is 2, 1. I verify it's right, and I put it in. That's great. So why is this so hard? Where's the drawback? Well, the problem is that we don't usually actually solve systems of equations using graphing because there's a problem. And we can see it right here. See that point of intersection now? What is it? I don't know. I could tell before because it was right on this grid line that it was at 2, 1. But now it's happening inside of a square. So what is that value? I don't know. I could hover over it, and basically what's going to happen is Desmos is going to give me like a decimal approximation, but very often it's an inexact answer. It's an approximation, not the actual answer. And when you're doing research or you're doing something to keep your business running, you don't want things that are like kind of the answer. You want the answer, right? If you're trying to maximize profit, you want to maximize profit. If you're trying to figure out the right dosage to get it you could just, it makes sense. When we're calculating dosages, do you want to be like, we'll kind of like roughly get near the right dosage, or do you want to give the right dosage? You want to give the right dosage, right? You don't want to do the wrong thing. So we want to make sure that we're as exact as possible, and frequently we cannot be very exact when we are using the graphing utility because we don't really know what that solution is. So that is why we will be transitioning to algebraic methods. When people solve systems of equations by hand, you're usually going to use algebraic methods, substitution or elimination, and then that's how we do it. But understanding how these graphs work can be very, very helpful in making sense of everything, because when you're doing the algebra, substitution, and elimination, it's very easy to get lost in all of it. In fact, you can kind of memorize stuff somewhat, because, like you'll memorize the steps because it's kind of the same thing every time. So you're just going through doing it. The algebra is a little different each time, but your steps are the same. And it's really easy to get to a point where you just kind of wake up and you're like, okay, I got my X and Y values, but like, what do those mean again? What am I even doing? Like, what are we talking about here? If you can visualize the kind of stuff we're talking about on the graph, it should make more sense to you, hopefully. Okay. Now, I mentioned earlier there's 3 types of solutions that we can get. And we're looking at one of them right now. This is the most common one. You have 2 equations and 2 variables, and you have 1 solution. That's what's going to happen most of the time. Okay? This is like probably 90% of the time, this is what's going to happen. But you can also get this. Okay, what do I have here? 2 parallel lines. So let's think about that a minute. We just decided that the solution to the system of equations was the intersection point of the 2 lines. But parallel lines don't have an intersection point. So what is the conclusion? What is the logical conclusion? Well, then there must be no solution. If the solution is the intersection point, and our system has no intersection point, then our only conclusion can be no solution, right? This is the part I was talking about. Well, there's lots of parts, but where people try to just solely memorize it without understanding, and then they get mixed up and give the wrong answer at the end. So if you can remember, oh yeah, parallel lines don't have an intersection point. The intersection point is the solution. Therefore, this means no solution. It's going to look different because most of the problems you do with systems of equations, you're not going to graph them. So you won't be able to see that they're parallel lines until you do a little bit of work, but then you want to remember and go, oh, these are like those parallel lines, so there must be no solution, and you give the right answer. Instead of doing, like I see this on this type of problem, all this work that's correct to solve the system, and then the conclusion is incorrect. And it's a bummer to do all your work right and then end up with the wrong conclusion and miss. For a problem like this, that's most of the points, is getting the right conclusion. That's the whole point of that problem. Okay. We'll take a look at this. We'll do an example when we get there. But the way this looks is like you'll end up with something like this. 0 equals 4. That's how it's going to look when we do it algebraically. So when you have a no solution graphically, it looks like this, 2 parallel lines. When you do it algebraically, you'll end up with a statement that has no variables in it, but it's a false statement, like 0 equals 4 or -3 equals 7 or something like that. You can't make 0 equal 4. There's nothing you can do that makes 0 equal 4. Those are just fundamentally different things. So that's what that's going to look like. Let me double check something really quick. Oh, right. So let's kind of take a look. Oh, before we do that, let's do this one other thing. The third option is that, and this is going to sound silly at first. I remember thinking like, why would you even do that? You know, because there wasn't a lot of explanation when I was learning this. Excuse me. So you've got the third option for your systems of equations could look something like this. Okay. Now, when you first look at those two equations, I suspect that most of us aren't going to recognize that they're the same equation. They look very different. They've got different numbers in them. They're in a different order. There's really nothing to indicate to us at first that, wait a minute, aren't those really the same equation? But notice when I graph them, then it's very obvious. Oh, yeah, look. They're just the same equation here. They look different, but they're the same equation. So you go, well, that seems silly. Why would you construct a system of equations that use the same equation twice? Why would you put it in there again? And the answer is that usually you don't do it on purpose, right? Maybe your business has two constraints on it, and you don't realize they're really coming from the same thing, and so you're solving a system, and then you go, wait a minute, I have the same equation in here twice? You don't usually know it. The other thing is, later on down the road, depending on what math you take, you get into more complicated systems of equations, and this concept here can get way more complex. So you can start to construct equations that aren't just a duplicate of another one, but a combination of two other equations, right? So maybe we have 3 equations. You're going to do a little bit of that in this class. Maybe your third equation is the first equation plus the second equation. Well, you're probably not going to recognize that out of the gate, but you get what we call a dependency. The third equation is dependent on the first 2, and then you can have some weird stuff go on. It can be powerful. Like in one of my classes, we do a problem like what I'm describing, and we use it to solve a traffic problem, right? So it can be useful, but we're kind of just going to do the basics with it in this class. Okay, so just recognize that's the third outcome, as you accidentally graph the same line twice. Well, let's think about what that would mean. If I have 2 lines on top of each other, let's see, 2 lines are on top of each other, so how many points do they have in common, right? That's what we're looking for, is points that are shared by both lines. Well, every point on the line is shared by the other line because they're actually the same line, right? They're the same thing. So that means every point is a point of intersection. Every point is a solution to the system, meaning there's an infinite number of solutions. Okay, so you want to kind of tell the difference between no solution and infinite number of solutions. When you get an infinite number of solutions, remember for no solution, the example I gave was you might see something like 0 equals 4, which is incorrect. For a problem like this, you might get something like 5 equals 5. The variables are gone, but you get a true statement. That means there's an infinite number of solutions. So you want to be comfortable with that, and again, think it out. No solution is pretty clearly where the equations don't equal, because there's nothing you can do to make 0 equal 4. But 5 equals 5 means you're going to get equality no matter what you do, no matter what you plug in. So there's an infinite number of those types of solutions. Okay. Okay, so let's do an example from the homework. So what does this look like? Solve linear systems graphically. So solve the following systems of equations graphically on the set of axes below. Okay, let's work through one. So this first one I want to do, let me make this a little smaller so we can look at the whole thing. Also, remember to read the directions. A lot of students skip reading directions, but if you read the directions, it'll save you a lot of time. Like I'll get students that'll email me like, how do I delete a line on Delta Math? Well, they tell you in the problem, click a line to delete it, and then you'll save yourself having to wait a day to get my response back, right? So solve the following systems of equations graphically on the set of axes below. Okay, this first one, Well, I figure I'll just use slope-intercept form to graph it because why not? That's a pretty easy way of graphing things. It's easier than plotting points. So I go to 0, -7. So 0, -7 is here, and you click it. And then notice now it's waiting for me to click a second point so I can define where the line is. Okay, well, what is this? My slope is -6/5. That's the rise over the run. Now with a negative, be careful. Remember that negative either has to go in the top or it has to go in the bottom. You can put it in either one of those places, but it has to go in one. In other words, we could think of this as -6 over +5, or we can think of this as +6 over -5. Either way, I'll actually show you both. So let me start. Oh, we can't because one way is going to take us off the graph. But that's another good reason why you would choose one over the other. I can't go down 6. There's not enough room on the graph. So what I'm going to do instead is go up 6 and to the left 5. So I'm thinking of it as +6 over -5. So that makes my run 6. So up 1. And then I'm going -5 because the negative's on the bottom. So 1, 2, 3, 4, 5. And I click. And there's my line. Okay. Now for the second one. Y equals 2/5 x plus 1. Okay, that means my intercept is at 0, 1. And then I'm going to go up 2 and over 5. 1, 2, 3, 4, 5. So I've got my two lines graphed there. And great news, we got ourselves a point of intersection. And that looks like it happens at -5, -1. So now I put that in here. Now remember, if we have a couple of ways that we can write solutions to systems of equations. One way is to write x equals -5, y equals -1. The other way is to write that as a point because we can interpret the solution as an intersection point. So we're going to write -5, -1. Yep, and I got it right. So you got your graph, you got your intersection point, you're good to go. Okay, and then you're just gonna do that like 5 times. Try to get it right because otherwise you have to do extra problems. But that's how those go. So nothing too tricky there. What about solve linear systems graphically level 2? Let's see, what's the challenge here? Looks like the main challenge is they don't give you the problems both in y equals mx plus b form, the slope intercept form. They do it a little differently, but that's okay. Let's go through this one. So this one I'm going to use the slope intercept form. I'm going to go to 0, -4, and then I'm going to go what? Up 1 over 2. So there's the first line. Well, this one's not in slope intercept form, so how am I supposed to solve it? Well, it'd be easy enough to put in slope intercept form. All you'd have to do is subtract x from both sides. So you could put the equation in slope intercept form. That's a good idea. The other thing you could do is use a table like we did earlier. That is, you're going to pick some x values and figure out what the y value is, and you're going to plot the point from there. So what if I plug in 0 for x? What does y become? Well, if x is 0, then y is -7. So it'd be 0, -7. So I put my point there. All right, well, what if we put in 0 for y? Well, then my x would be -7. So we put it there, and it looks like my point of intersection is -2, -5. And there we go. So it's the same game. You just have to use your graphing skills in order to get it done. Okay. So that's how those go. You just graph those lines, look at the intersection point, call it out. Okay. And this is just writing the system. Okay, here is some problems that students definitely find confusing, but it's good. They're really good to work on because really a lot of what you want to learn from mathematics is critical thinking. The truth is that's a lot of what you're going to take forward into the world that's going to help you. I mean, in this class, obviously, all the dosage stuff we're going to do later is helpful. But also, one of the reasons math classes are helpful is they help you think in a reasonable way, right? There are some subjects where, you know, emotion and social aspects and empathy and that kind of stuff can be really important, a really important part of the conversation, right? But a lot of times things are sciencey and mathy, and, you know, they're not really subjective, and sometimes we're not, you know, people's feelings are not really part of the conversation. Sometimes that's appropriate, but sometimes we just need to do some calculations and figure out what's going on. Well, that takes critical thinking. That takes logical, reasonable, organizational skills. It takes a lot of skills to be able to work through math stuff. And those skills, when you learn them, can definitely carry over later into life and be beneficial in other ways where you need to be logical and reasonable and sort of objectively calculate things. Okay, so here you're going to be defining your variables and creating your system of equations. Now, many of you and many people go through this system and they just, I've handed you a system and now you're going to solve it. Okay, now I'm giving you another system, solve it. Now another system, solve it. And there's merit to that when you're learning how to solve a system of equations, but it doesn't work that way in real life, right? I've never heard of a situation where someone is sitting there and someone else comes by and says, hey, I got this system of equations, solve it and get back to me. Like, that doesn't happen, okay? So it's kind of silly that that's what we make the homework be, or the lesson is that we teach you how to solve systems of equations, but then you don't really get like why or where it came from or how, because in real life that's like the hardest part, is the where did the system of equations come from. So it's really important that you be able to take a problem and convert it to systems of equations and figure it out that way. So we're going to do that here. We're going to convert this into the variables and the systems of equations needed. Now, this here, I will tell you, where we define the variable, one of the most important parts of the entire problem. And it's one that people try to skip all the time, right? And I know, you hear me harp on this, go slow to go fast. Take your time and do the job right, and it's actually going to be faster than trying to speed your way through the problem and get it over with. Okay? Now, why would that be? Well, this is a regular thing that happens when I'm teaching systems of equations and then I have students working on some problems. Someone will call me over and go, I don't know how to come up with the equation. And I go, okay, well, what do your variables represent? And they go, I don't know. Actually, sometimes I'll say, well, did you read the problem? And they'll say, no, I didn't read it. Well, you kind of have to read it. So that's actually step one, is you want to read the problem. And then sometimes you go, okay, I'm going to read through it. You know, they read through it really fast and go, okay, I read it. Do you understand it? No, I don't understand most of what it says. Okay, so what you have to do is break it down and reread it. You got to break, you know, even me, when I do a problem like this, you'll probably see when I'm talking about it, there's probably going to be sentences in there that I read 2 or 3 times. Why? Because you can't catch all the information that fast. Mathematics comes at you quickly when it's written, right? Like, you're in a history class and you want to, like, you're reading about, like, you're working on, like, the Reconstruction era or something of U.S. history. Well, you're reading this book that's telling you essentially a story about the Reconstruction era. You can almost read it like a novel, right? A history book can oftentimes be read like you read a novel, where you're just going through it. You're reading paragraph, word after word. Okay, I get it. I just read 30 pages and I understand that Reconstruction a lot better now. People don't generally sit down and just start to finish read 30 pages of a math book or a math problem or whatever, because the information is coming so quickly at you that you just can't digest it as fast as you can as a story about Reconstruction. Okay? So what you have to do here is, like, just read the first sentence. A paper company needs to ship paper to a large printing business. Do I understand that? Yeah, okay. There's a paper company. They got to ship paper to something else. Okay, good. The paper will be shipped in small boxes and large boxes. Okay, still pretty good. We got small boxes. We got large boxes. Okay, I got that. Each small box of paper weighs 40 pounds and each large box of paper weighs 70 pounds. A total of 20 boxes of paper were shipped weighing 1,220 pounds altogether. Okay, wait a minute. What just happened? I don't know. There's a lot of numbers and words coming at me pretty quickly. I better read that again. Okay, let me see. What do we got? Each small box of paper weighs 40 pounds and each large box weighs 70 pounds. Okay, so the two different size boxes make sense. When we put paper in them, they're going to have different weights. Okay, the weights are 40 and 70. Okay, got that. Okay, I read it again and I understand it better now. Okay, a total of 20 boxes of paper were shipped. Okay, so we have a total number of boxes now. Okay, got it. Weighing 1,220 pounds altogether. Ooh, we have a weight total too. So we have a box total and we have a weight total. Okay, got it. Write a system of equations that could be used to determine the number of small boxes shipped and the number of large boxes shipped. Okay, so we're supposed to find out how many boxes of each type was shipped. Got it. Okay. Okay, so see how it wasn't just start at A at the beginning of the problem and then stop when I get down to that period at the end and I've read it once and understand it. You got to read it till you comprehend it. Okay? All right. So now what do? We want to pick variables. Now frequently we can pick variables like X and Y, and that's fine. But sometimes we want to be a little smarter and pick better variables. So what variables should I pick? How about variables that are going to help me remember what it represents? That's good, because if you just pick X and Y, it's very easy to mix up your answers at the end of the problem, right? And like sometimes people will go like, well, but I mostly got it right because I got the right numbers, I just switched them. But like if you think about it, if you're at work and like, you know, you figure out two dosages, but you switch them, it's probably not going to go well, right? You just calculated two patients' dosages. You calculated it correctly, but then you switched them and gave the wrong amount to each person. No one's going to care that you're like, well, my math is right. I just gave it to the wrong person. That's going to be a big problem, right? So it's really important that not only do you do the work right, but that you make sure you understand which variable that number goes to. So sometimes we can be better, and instead of choosing X and Y, why don't I choose S and L? S would represent the small boxes and L would be for large boxes. So, I mean, that's not the full definition, but that's how I'm remembering. S is small, L is large. Now, I'm probably not going to mix them up at the end of the problem and go, oh, I think S is my large boxes and L is my small boxes, right? We're not going to mix that up because we call them S and L. Okay? All right. So now there's a tendency here when we define the variable for people to go, well, S equals small boxes and L equals large boxes. Well, what do you mean S equals small boxes? What is it about the small boxes that S is representing? You have to give not just the object, but also the characteristic that you're measuring about that object. So in other words, there's some choices here. The volume of the small box, the weight of the small box, the number of the small box. See how there's three different choices? And if you just say, well, S is small boxes, well, it's pretty ambiguous as to what you're even talking about. S is a variable. It's not literally a small box. It's a representation of a measurement of the small boxes. Do we want the volume, the weight, or the number? In this case, they want us to calculate the number of boxes. So that's also our unknown. It's probably a good idea to go with that. So I'm going to go with the number of small boxes. Okay. See how that explanation is just better. We didn't say S's box, small boxes. That's I don't know what you're talking about then. The weight, the volume, the number? The number. Okay. Now I understand what you're talking about. By the same reasoning, L would be the number of large boxes. Okay. People like to skip this step where they either don't know what the variables are or they don't write them down. By not writing them down, you're very likely going to end up making a mistake later on, even if most or all of your work is correct. So just write them down. It's hugely helpful, right? But I'll get this where students call me over and they're like, I don't know how to write the systems. And I'll be like, did you read the problem? Yeah, I understand the problem. Okay. What are your variables? I don't know. I don't know. I didn't come up with any variables. Well, how can you make an equation that involves variables if you didn't define what the variables were, right? It'd be like you go to build a house and you go there and you're all ready to build the house, and then someone's helping you and they're like, well, what are you building the house out of? You're like, I don't know. I haven't decided. I don't know if it's going to be brick or wood or concrete or who knows, but I'm trying to build this house, but it's not working. Well, yeah, because you haven't planned, you haven't done the plan of like what you're building the house out of. Well, it's the same thing here. We're trying to build equations, but if you haven't done the part to decide what you're building the equations out of, then how would you expect to be able to put those equations together? So don't skip this step, and don't skip writing it down. It's the same thing where I see students that are like, no, I know what the variables are. Okay, what are they? Oh, I forgot. Well, write them down. Just write them down on the paper. It only takes a few seconds. Now that we have those building blocks, now we can start to put it together. So now what you want to do is go back and you read the paragraph and try to take information that's encoded in that paragraph, and we're going to translate that into an equation. Now, usually there's one of these that's a little bit trickier, and one that if you recognize how to find it is easier, because usually these are based on totals. So we have a sentence in here that gave us some totals. In fact, it even uses the word total. Okay. A total of 20 boxes of paper were shipped. Okay, stop right there. Can we make an equation out of that? A total of 20 boxes of paper were shipped. Okay, so we shipped small and large boxes of paper, and we have representations for the number of small and large boxes. S is the number of small boxes. L is the number of large boxes. And I know that 20 boxes were shipped. So is there an equation there? Well, let's see. If I take the number of small boxes and I add to it the number of large boxes, then what should that equal? Well, the problem tells us there was a total of 20 boxes shipped. So that equation should be S plus L equals 20. So always try to look, a lot of these problems that you see on the homework, they're going to have a total hidden in there that's just going to end up being, not every problem, but many of them, it's just going to be the two variables added together equal some total. So that's, again, why it's important here to write the number of small boxes shipped, because if you just write, oh, boxes, small boxes, you're not going to recognize, oh, I think that's maybe connected to this total number of boxes. Maybe I can construct my equation from those things. Okay. All right, the next piece is a combination. It's a mixture. You may have heard of mixture problems before. It's a mixture of things, which is slightly trickier to put together, but this is another pattern you're going to see in a lot of problems. So you want to see if there's a way you can write an equation relating to what I'm about to show you. Okay, so we got a second ago, we talked about a total of 20 boxes of paper were shipped. Okay, that we just made an equation from that. Weighing 1,220 pounds altogether. Okay, so we just got a total weight. So imagine you're looking in the back of a big work truck, and there's 20 boxes of paper back there. The small ones weigh 40 apiece, and the large ones weigh 70 pounds apiece. So 40 pounds and 70 pounds for these boxes of paper, and we know we have 1,220 pounds altogether. Well, let's break this down into pieces. Instead of getting confused and trying to figure out, like, how am I supposed to figure out how these things work together, just worry about one at a time. What if we just wanted to know how much weight there was from the small boxes? What would you do? Well, each small box weighs 40 pounds, and if I knew how many small boxes there were, then I could multiply 40 times the number of small boxes and get the paper weight from the small boxes. But we don't know how many number of small boxes there are. That's what we're supposed to figure out. But luckily for us, we defined one of our variables to be the number of small boxes. So the weight from the small boxes is 40S, 40 times S. For each of the S boxes, there's 40 pounds of paper sitting there, right? By the same reasoning, how would we figure out the amount of paper from the weight of the paper from the 70-pound boxes? Well, I would count up the number of large boxes, and I would multiply by 70. But again, we don't know the number of large boxes. That's the whole point of the problem. But we do have a way of representing it with an L. So 70L equals, what are these supposed to equal? Well, the total weight is 1,220. So these should be our variables. These should be our equations. Let's take a look, see if I did it right. There we go, green check. Right? So you can see they basically have the same stuff that we just put together. You get your answer, and then you're going to go on and you're going to do a very similar one. The same idea. Okay? I don't have time to do another one, or we'd take a look at it. So that's where you're putting the systems together, and it's so important. I know a lot of times people are like, I don't like the word problems where I got to read stuff, but you know, the way I've heard it put the best that I think is the best is, you know, people will say, in real life, everything is a word problem. There's never a time when you just run across an equation, you're like, oh, I think I'm going to solve this. Like, if you're at your job and you're solving an equation, you're probably the one who came up with the equation. If you're doing research or trying to figure out your personal finances or retirement or a loan, you're probably the one who has to construct the equations and then solve them. So you have to be able to do both sides of that. Okay, systems of equations. Now, how do we actually solve systems of equations? So there's two methods. And why do we teach two methods? Why can't we just use one? And the answer is that each of the two methods that we learn for solving systems of equations can be used for every system of equations. So we have two methods, substitution and elimination. You can do every single system of equations with substitution. You can do every single system of equations with elimination. But a lot of times, one of those ways is significantly easier than the other one. Meaning that if you don't know how to do both of these, you're going to end up doing way, way more work in certain problems than you need to. So it's a lot more convenient if you just know how to do both, and then you can work through them. Plus, the ideas that we use in these problems get used in other areas of mathematics. So if you already understand this, there'll be times when you learn something else and you're like, oh, that's kind of like substitution. Okay, that's not too bad then, and you get it. I know it seems like a lot at first, but once you do some of these, you're like, okay, I get it. I'm good with this. So let's take a look. Let's do level 3 since there's not much time. Actually, that wasn't what I thought it was going to give me. That wasn't either. I thought there was one where I don't want to. That one's too straightforward. Let's do this one. So how does this work? How does substitution work? So I'm going to walk through a problem. Let's do negative 10x plus 3y equals 34. Oh, did I close my overleaf? Was it negative 10x plus something equals 34? That's definitely not right. What was it? Negative 10x plus 3y plus 3y equals 34. Then y equals negative 8x. Okay. Okay, and then you'll see what I'm doing now is just double checking that I got them written down correctly. I will tell you a significant portion of the time, like maybe half the time, that someone calls me over and says, I keep doing this system of equations, it's not coming out right. What am I doing wrong? We look, and the problem is that they wrote the problem down wrong. So they were doing the work right, they were just doing it on the wrong problem. So it's worth like 1 extra second to just go back and double check, like, okay, did I write this right? Because one little mistake at the beginning will make your next 10 minutes useless of you trying to solve that equation, or 5 minutes. Just throw it in the trash because you were doing the wrong problem. So double check that it's right. Okay, step 1 now. What do we do to actually go through and solve this? So step 1, you're going to solve for One variable. So what does that mean? It means you're going to look in these two equations and see if you can isolate one of the variables, get it solved for all by itself. Luckily for us, this problem already has that. The second equation is already solved for y. Y is all by itself, right? And then sometimes somebody's like, somebody will be like, well, what about x? X is solved for. No, the x term is by itself, but it's not solved for. It's not x equals, it's negative 8x equals. So it's not sufficiently solved for. If you wanted to, you could. You'd have to divide both sides by negative 8, and then you'd end up with fractions. But you could solve for x if you wanted. But we probably just want to go with what we have here. Y is already solved for. Let's go with that. Okay, good. So in this particular problem, the variable was solved for. We'll use that. But just recognize that sometimes you have to solve for that variable. You know, but you've done this before. We did this all the time in algebra. Solve for this particular variable, you know. Okay, step 2. Now we're going to substitute into the other equation. You have to use both equations. So the one that gives you your substitution, in this case the second one, we have to substitute into the other equation. So you have to, at this point, both equations should be involved. Okay, so if we use the top one to get our substitution, then we would substitute into the bottom equation. We're getting both of them involved. So what does that look like? Well, it's going to look like I'm going to take the top equation, but our substitution is that y is equal to negative 8x. So when I write that top equation, instead of writing y, I'm going to write negative 8x, right? That's the substitution part. I'm substituting. We know that y is equal to negative 8x, so it doesn't matter whether I write y or whether I write negative 8x. They're both true because they're equal to each other. But it's beneficial to us to write it as negative 8x, and I'll show you why in just a second. So I'm going to write negative 10x plus 3, and I'm going to put this in parentheses because if you don't, people mess up the distribution. Sometimes there's a distributive property that has to take place. So just put it in parentheses. It's very common when you substitute to put them in parentheses, and it'll save you a lot of mistakes. So this becomes negative 8x equals 34. So can you see how this is, as soon as it compiles? This is just the number one equation, but instead of writing my y, the second equation told us that y was equal to negative 8x, and we wrote it right there. You see how the y just turned into the negative 8x? We're like, well, fine, if they're the same, I'm going to write it this other way, right? Now, why did we do that? You go, okay, well, I understand. You solve for one variable, and you substitute it in there. Why? Well, look what we have here. We started off with equations that had two variables, and we now have one equation that has one variable. Wait a minute, I know how to solve those. I learned that back in beginning algebra. We solved equations that had one variable. I know how to do that. Yeah, that's the point, is we took an equation that we didn't know how to solve, we turned it into one equation with one variable, and now we know how to solve it. Okay, so now you go about doing that. Okay, so I've got what? Negative 10x. This is going to be minus 24x, right? So negative 10x minus 24x, guess what that's going to be? Negative 34x equals 34, meaning that x equals negative 1. So x is negative 1. Okay. Now there's a tendency for people to stop here and go, cool, I'm done. Not really. Remember back over here, what do our solutions look like? The solutions are points. The solutions have two coordinates, an x value and a y value. So if you've only found one of those, you've only done half the problem. Actually, you've done more than half the work, but you only have half the solution. So we want an x value and a y value. So we got the x value. How do I get the y value? Well, this part from here on out, the rest of the problem is the same for both substitution and elimination. What you're going to go is you're going to go back to the original system that you started with at the top, and you grab whichever one you think is easier. I'm going to go with number 2. And then you're going to substitute this x value in there. So if I do that, this becomes y equals -8 times -1. Right? See how I've, inside the parentheses, I turned the x from up here into the -1 that we know x is equal to, meaning that now we know that y equals 8. Okay, y equals 8. So now we know both coordinates. We have found the full solution. If we were writing it as a point, it would be -1, 8. Or also we could think of it as x equals -1, y equals 8. So let's put it in here. And they give it to you like a point. So you go -1. Remember, your x goes first, your y goes second, just like when you're plotting a point. Hit submit. Oh, also remember, if like, I'm pretty sure I got it right, and we're low on time, so I want to move ahead. But it's worth your time to plug this into both equations and make sure it works, so you know you got it right. Otherwise, you might have, if you get it wrong, you're going to have to do an extra problem, right? So double check that work before you put it in there. And that's what you have to do in real life, right? In real life, there is no back of the book with the odds in it that you can like see if your answer's right. In real life, you're either going to take out that loan or plan for your retirement or whatever it is that you're trying to calculate, and you're just going to do it and hope I did that right. I hope I don't get to retirement and realize I didn't carry a 1 or something. You know, you want to double check your work and make sure that you did it correctly. And there you go. Green check. So you can see they did it the same way we did. They substituted in for here, right? It looks just like the work we did. Get down to x equals -1, substitute in there, you get your answer. So that's how substitution works, okay? Go back here. You will have linear systems in 3 variables. This one, I actually don't like teaching this in algebra. A lot of times it's optional, but the course outline says I have to teach it. So I only make you do a couple of those. So work through it, know how to do it. I won't put the 3 variable one on a test. I don't like putting those on tests. But do these homework problems, and then we can say that we went over it and learned how to do it. But you know, there's kind of this. I'm not a big fan of like secrets, and some people want to keep this all secret. The reality is there's more and more software coming up that will do calculations for us. There's stuff that's going to do systems of equations for you. Like, you know, if it's the little ones we're doing, the amount of time it takes it to put it in a computer is about as much work as just solving the system of equations by hand. But by the time you get to 3 variables and 3 equations, 4 variables and 4 equations, it's better to just have a computer do it for you. So just kind of be aware of that. So you might go, well, wait a minute, then why are you making us learn how to do these systems of equations? Because sometimes you do have to do them on the fly, like where you're maybe not sitting in front of a piece of software that will do the calculation for you. And plus, it helps you understand what you're actually doing. And again, math is useless if you don't understand what you're doing, right? It's kind of like you have to earn the right to have a computer do it for you. Because I see all the time where people, like, they memorize how to do stuff on a calculator, but they have no idea what they're doing. They're like, well, I know how to get the answer you want. Okay, but can you explain to me what it means? No. And this class is about as applied as it gets. Everything we're doing in this class is to get you to be able to give accurate, reliable dosages to the patients that you're going to be dealing with. Pretty important. Right? It's kind of a big deal that you get that right. So it's really important that we can do this math correctly and that you understand what you're doing when you use the mathematics, because otherwise you're never going to be able to remember how to do anything if you don't understand it. So do that, but I'm not going to put the 3 variable one on the test, but you should take a look. Watch the video on how to do that. I don't have enough time to go over it, but watch the video on how to do that. So let's see, this is probably not the one that I want. That's not the one I'm looking for. Equivalent systems, what is that? That's where the system of equation will look different, but it's really just a different version of this one. Remember, there's always the help videos up here. I think if you watch the help video, this part will be fine. I think the things I'm thinking about are mixed in, but let's do an example like the following. Let's do another system, and I'll show you what this looks like. Remember we talked about those weird solutions? So let's say that you want to solve the system of equations, that is 2x plus 3y equals 6, and 4x equals negative 6y plus, minus 7. Okay, so this is our system of equations right here. Actually, let's do this one as, let's make this, let me change this, 4, and we'll make this 8. Okay, so we've got this system right here, and I want to go through and solve this using substitution. I have just enough time to show you this. So, okay. We don't have one of the variables solved for us, so I have to solve for one of the variables. So I think what I'm going to do, I'm going to take that first equation and divide everything by 2. That will make it x plus 2y equals 3. Right? So I just took equation 1 and I divided it by 2. X plus 2y equals 3. Okay? And then what I can do is just solve for x. When you're choosing to use substitution, if you choose a variable that has an coefficient of 1 or negative 1 on it, those are the easiest one to solve for. Otherwise, sometimes you end up introducing fractions, which just makes it harder. So if I solve for x, this would become x equals negative 2y plus 3. And now we can do our substitution. So wherever there's an x, I can write it as negative 2y plus 3. So let's remember, which one did I get this from? This was from the first equation, right? So that means I have to do my substitution into the second equation. Okay, so if I do that, in the second equation, I'm going to get 4. But now I'm going to write in parentheses what x is equal to. Negative 2y plus 3 equals negative 2y plus 3 on this side. Wait, that's not right. Sorry, I was looking at the wrong line. I knew that didn't sound right. Negative 8y minus 7. So it's the second half of the second equation. Sorry if I confused anyone. I was looking at the wrong line there. Okay, so I took line 2, and where there was an x, we just replaced it with the expression of what x is equal to. Okay, makes sense? So we're using that substitution. So now we're going to simplify, and that's going to give us negative 8y plus 12 equals negative 8y minus 7. And to some of you, that might have already sounded a little strange, and that's because it is. What happens when I add 8y to both sides? Well, the 8y's go away, and I get 12 equals negative 7. 12 equals negative 7. What are you talking about? 12 doesn't equal negative 7. Negative 7 equals negative 7, and 12 equals 12. What do you mean negative 12 equals 7? Oh, there's a good question in chat. I'll answer that in just a second. So remember, I kind of suggested this earlier. When you get to this where there's no variable and the equation is false, then it's just false, always false, right? Remember, a solution is true. It works when we can make an equation true. How can you make 12 equal negative 7? You cannot. And there's no variable to allow us to like change values. 12 equals negative 7, that can never happen. So your conclusion is no solution. There is no solution to this system of equation. And although we didn't recognize it early on, if we graphed these, they would be parallel lines. Okay? Good question here in chat. Do you have to write negative 2y plus 3, or can it be 3 minus 2y? That's a good question. As long as you keep the sign with the right term, then you can write it in either order. Okay. What you can't do is rearrange the terms and not keep the signs consistent. So you couldn't write it as -3 plus 2y. That's a thing I see people do, and it's because they're not moving the sign with the term. But yes, what April asked about on there, that's a perfectly legitimate way to do it, and the problem will still work correctly. Okay, but you got to move that sign in front of the coefficient with, the sign is part of the coefficient, so you got to move it with that. As long as you move the sign, you're good to go. If we had done this and we had gotten 12 equals 12, that's when it would be an infinite number of solutions. Okay, that's that other weird answer that we get once in a while. Most of the time you're going to get a single solution, okay? So so that's what you want to look out for. Let's see. Okay, so we didn't have time to cover elimination. We should have plenty of time for me to cover it next time, because this homework's not due for a while, right? Yeah, this homework's not due till later in February. Now, again, don't wait till the due dates to do this. If we're covering it, just start working on it, because I'm pretty generous with my due dates, because I'm not really one for extending due dates. So if I've given you 3 weeks to do a homework, then I'm not real sympathetic when you tell me like, oh, sorry, I got sick last night. Like, well, you had 3 weeks to do it. If you're doing it the last minute, that's kind of on you. So, but I realize people do get sick. People have stuff going on, but it's not a good life habit to do stuff at the last minute. Usually means you're going to do a bad job on it. So don't wait until this is due to work on the homework. You'll probably forget half the stuff I talked about if you wait, right? Plus we're going to be moving ahead into new stuff. So I probably will be able to talk about elimination a little bit next week when we're meeting in person. But also, if you watch the videos, I bet most of you will be able to figure out elimination from watching the video. So if you wanted to move ahead and get a bunch of this work done, you could probably do it. I think at this point we've seen enough that you probably have a pretty good understanding of systems of equations. Now, if you're a little confused and you're a little fuzzy, that's fine. Like, don't feel bad about that. I gave you a lot of new information, and it takes time for this stuff to sink in. So go ahead, let it sink in, think about it, work on the homework. Don't worry if you're still piecing things together. But by working on the homework in the near future, it's going to start to make a whole lot more sense to you. Okay? So please remember, next time we meet, we will be meeting in person on campus in room 230 in the science building. That will be not very far from the parking lot. Again, it's been years since I taught there, so I can't remember which side of the building it's on. It'll be almost 2 years since I've been teaching in there. But it's near that parking lot where they have the market. And that parking lot now has like solar panels over it, so your car won't even get hot when you're in the classroom. So you can park there. And I think, last I heard, I think maybe you don't even need a permit this semester or something. Double check. There should be a sign. So don't get a parking ticket because of what I said. But I think they might not be making us get permits. I have to get a teacher permit, and then other people get like the student permit. But I think that's how that. I think so. So just watch. See if there's a sign that says like you don't have to pay right now or something. Okay. Otherwise, I will see you a week from today in the classroom. Remember, I have office hours. There is the tutoring center, and all that kind of stuff. So make sure you're getting the help. This is one thing that I'm seeing about this class is we move quick, and we're only yeah, thanks. That's what I thought is we didn't need one for this semester. So, but we move quick in this class, so don't wait for those due dates because we're going to learn a bunch of stuff before then. If you're waiting for the due dates, you're always going to be kind of behind. And we got to make sure we leave plenty of time for the dosages part of the class, the math for meds part. Okay, so the class is one that faces the parking lot. Okay, thanks. It's been too many years. I couldn't remember. They put the odd numbers on one side of the building and the even numbers on one side, and I can never remember which side we're on. So I think this is one of those rooms where I can't open the windows, which means we're going to open the door. So that we can get some ventilation in there and reduce the risk of any asymptomatic people infecting everybody. So, but we will, yeah, I'll see you there in a week. So please be prepared for that. And stick around in Zoom if you have any questions for me. Otherwise, I will see you next week. It'll be nice to see some actual humans and not just black rectangles in the Zoom meeting. So, okay, thanks everybody.